Right, well, 5 o'clock here. So good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast. And good evening to anyone joining us from Europe or stations further east. And a very warm welcome to you all. From a nice sunny London, I should be outside in the garden drinking beer and mowing my lawn, but here I am talking to you guys. Thank you for joining this, the 40th of our regular series of short courses on pumping topics. We've been doing these for over 4 years now. Amazing how the time flies. This one's going to last about 35 to 40 minutes, allowing us plenty of time for a Q&A session at the end. So let me restart the share. Well, here is a listing of the previous short courses we have run during the last 2 years. If you've missed any of them, you can get a copy of the materials from our website. Go to www.ruhrpumpen.com and follow the link to RP short courses. If you go to ruhrpumpen.com, you get to this page. And here is the link to RP short courses. If you click on that, you get to this screen, where you will see all of the recent courses listed. Here in this slide, I just show the latest 4. But on the website, you'll see all of them, and you can click on any of these links to download the course material for your viewing at your leisure. Well, today's seminar is going to look at vertical pumps. I quickly realized that this was too big a subject to cover in one 35 to 40-minute session, so I've divided it in 2. This week, we will cover VS1, VS2, and VS3. And in the next session, in 4 weeks' time, we'll cover VS4, 5, 6, and 7. We will, as usual, be holding a Q&A session at the end, so at any time you can post in the Q&A facility at the bottom of your screen to ask any questions or make any comments. I will address those that I can live at the end of the session, and the rest we'll address by mail in the coming days. We are recording this session and we'll make it available to all attendees as a YouTube link to the video, as well as by emailing you the PDF version of the slideshow and of the Q&A summary from both of today's sessions. So on with the course. An introduction. Well, here is our pedigree, Ruhrpumpen's qualifications, if you like. We have a wider range of vertical pumps than just about anyone. And I personally have been a vertical pump specialist virtually all my career, which dates back to 1980. So 44 years now, blimey, in my 45th year as a pump guy. So these are the vertical pump configurations as defined in API 610. VS1 being a diffuser type with discharge through the column. VS2 being a volute type, again with discharge through the column. VS3 being axial flow type. VS4 being a volute type sump pump with side discharge. VS5 is similar to VS4, but a cantilever design, which means it has a rigid, large diameter shaft and no line shaft bearings. And VS6 is a diffuser type double case pump. And VS7, volute type double case pump. So in today's session, we're going to look at VS1, VS2, VS3, and in the next session, we'll look at 4, 5, 6, and 7. So here's effectively the same slide, but a more visual representation of the pumps. The VS1, which is diffuser type, discharge through column. This also VS1. These are the radial or Francis vane impellers. This is more mixed flow, larger impellers. The VS2, the volute type, with suction at the top and at the bottom, double suction. again discharging into a central column. VS3, the axial flow pumps. VS4 and VS5, sump pumps. And VS6, I'm showing two different types here. This is the API type with the elliptical head, and this one is an industrial, less expensive version for water service industry. But because we like to maintain the educational value of these sessions and not just make them product placement, I want to give you a little bit of pump theory here for you. So here are the four common impeller types. Radial, meaning the flow exit from the impeller is essentially perpendicular to the shaft axis. With this design, you're generating the most pressure. At the other extreme is axial flow, meaning the flow exit from the impeller is parallel to the shaft. With this design, you generate little pressure. Largely, it's about high flow. Between these two extremes, we have mixed flow and Francis vane. Francis vane is a modified radial flow, giving smoother transition from entrance to exit. Slightly higher flows, slightly lower heads than radial. Now let's talk about specific speed. This can be considered to be a dimensionless number that describes the impeller head and flow performance. But actually it isn't dimensionless. It just doesn't have a useful dimension like revs per minute or meters per second. So it's best to think of it as dimensionless. Here is the formula, and the resultant number uniquely describes the impeller performance. So here is the previous slide showing the various impeller types and their specific speeds in US units, which is US gallons a minute, feet and RPM to calculate this figure. And above is the same in metric units, meter cubes per second, meter RPM. You'll see that the conversion factor between the two is 51.6, which is as close to 50 as makes no difference. So this is a very useful number to remember in your head if you start seeing specific speed numbers that you're not familiar with. Now, specific speed tells us a lot about curve shape. This is a little bit messy, so I'll take it slow. Radial impellers here on the left have flat HQ curves and a continuously rising power curve. Mixed flow impellers here have a steeper HQ curve and what we call a non-overloading power curve. Non-overloading means it peaks close to best efficiency point and it falls off to the left or the right of BEP. And finally, axial flow, which have a very steep HQ curve and a power curve that is highest at zero flow and drops as you get closer to best efficiency point. Now, a really neat coincidence is that when using metric units for specific speed, it tells you the steepness of the HQ curve. So, for example, a specific speed of 45 in metric units means a head rise to shutoff of about 145. Now, for those who are metrically challenged among us, here is the chart with US units added. Most of us are far more familiar with the US units than we are with the metric units. Now, what you'll also see is that radial impellers tend to have wider operating ranges than axial impellers. So this is another messy slide, so I'll take my time over it. Here are the operating ranges between these lines. Okay, these lines here are showing the operating ranges. A1 is excellent operating performance. A2 is very good. A3 is just good. And A4 is acceptable, so allowable. Okay, so here at the bottom we see a radial impeller with specific speed 16 in metric units, which is 800 in US units. It has an excellent operating range of 80 to 120% of BEP and a good operating range of 40 to 130. So that's pretty good. At the opposite end of this spectrum, here's an axial flow impeller with a specific speed of 256 in metric, 12,800 in US units. And it has an excellent operating range of 90 to 105% of BEP and a good range of only 70 to 110%. So a far more limited range than the radial impeller. And the Francis vane and mixed flow impellers are somewhere in between those. What else do we see? Well, here is a chart from the Hydraulic Institute showing specific speed along the x-axis here in American units and the pump efficiency on this axis. And what we see here are some radial pumps in the 500 to 1,000 specific speed range. And we see they're quite low efficiency, 50 to 60%. Some larger radial pumps that are a bit more efficient, but still pretty low. And some larger still radial pumps might get up as far as sort of 80%. But mixed flow pumps in the 2,000 to 3,000 range have much better efficiencies in the region of 90%. So if we go back to this slide again, and we see that the 2,000 to 3,000 specific speed corresponds to the Francis vane and mixed flow region. Here we've added the Ruhrpumpen pump types added, and you'll see a lot of pumps here in the Francis vane and mixed flow region. And that's why it's the optimum efficiency. These pumps are mixed flow, higher flows, and these PMR, that's an axial flow pump. Here is what some of those impeller designations look like. There's an open impeller, a semi-open impeller, that's quite important. Semi-open impeller has a back shroud, but no front shroud to it. We'll discuss that a little later. Here are single suction closed impeller with a back shroud and a front shroud. Here a double suction impeller, flow comes in that side and that side. Here a mixed flow impeller. And here an axial flow impeller. It's more like a propeller than an impeller. So let's move on now to static lift. Now this is a critical step in specifying a vertical pump. Make sure you've considered the static lift from the water level in the sump to the center line of the pump discharge flange. I've lost count of the number of times that it's not clear on a pump data sheet whether the TDH that's been given us includes or does not include this static lift. You can forgive an inexperienced process engineer for considering only the pressure required at the discharge flange. It's really up to us equipment engineers and applications and sales engineers to ensure that the static lift is considered. So what I would ask you specifying engineers to do is always add a note to the datasheet clarifying whether the static lift has been considered or not in the TDH. It can save a lot of mistakes and a lot of wasted time. So now looking at the pumps, VS1, VS3. Firstly, VS1. This is an overview slide. These are the lower flow Francis vane type pumps. Flows up to about 13,600 cubic meters an hour, which is 60,000 gallons a minute, and heads up to about 760 meters or 2,500 feet. It's a multi-stage centrifugal pump with diffuser type bowl. It can have either semi-open or enclosed impellers. It will often have a basket strainer, or if it's going down a borehole, it could have a conical strainer. The line shaft can be product or oil lubricated, and its standard materials, if it's in water service, would be cast iron bowls with bronze impellers and 416 stainless steel light impeller shaft. But that's just for fresh water. These are frequently used for seawater and more aggressive services like that, in which case they will frequently be supplied in, say, nickel, aluminium, bronze, or in stainless steel, or in duplex stainless steel, or even super duplex stainless steel. We supply them in all these materials now. Depends on the depth of your wallet. The discharge head, it would be cast iron on the smaller sizes or fabricated steel on the larger sizes. But again, of course, if it's in exotic materials, it will follow that as well. Bearing material would be bronze if it's in freshwater service, or it will be something like petrocoke or PTFE in seawater type service. Slightly larger ones, the mixed flow pumps rather than the Francis vane ones. These are, say, slightly larger. Some people consider them to be VS3 rather than VS1. It's API 610 isn't really clear where these fall. So the larger pumps flows to 50,000 cubic meters an hour, which is 220,000 gallons. Head to 175 meters, which is 575 feet. Pretty much the same. Again, can be made either in cast iron and steel for freshwater service or in more exotic materials for seawater. Mechanical seal can be fitted or packed gland. And now the VS3 type pump, the axial flow pump, flows up to about 73,000 cubic meters an hour, which is 320,000 gallons a minute, and heads to 27 meters, which is 90 feet. Low heads, of course, now, as we're talking axial flow pumps. Very high flows, very low heads. There's a range chart for all the VS1, VS3 pumps here. The blue are in metric units, the black are in US units. So here we see a large VS3 pump, two-stage bowl assembly. Here the column pipe, and here the discharge head, all nicely loaded on a low loader. Now the discharge heads can be above ground or below ground. Depends on the customer piping configuration. The larger ones will be a fabrication, and smaller ones might be a casting. Again, it can be made in any of the materials you need, fabricated steel, or it can be duplex stainless or super duplex. Smaller pumps, the Francis vane type VS1s, will probably have an L-shaped discharge, a right angle discharge. It'll either be above ground or below ground, again, depending on the customer piping arrangement. Again, a fabrication or a casting and any material you like. Now, the larger sizes, the mixed flow pumps and the axial flow pumps, will have a 3-piece or 5-piece mitre elbow to make it a smoother flow through there and minimize the losses. Here we see it can either be a mechanical seal or packed gland. The motor coupling type will depend on whether the pump thrust is accommodated in the motor or by a separate thrust bearing. All these pumps are designed to operate in down thrust so that the shaft is in tension, and if it were in compression, if it were operating in up thrust, then the shaft would whip and wipe out the bearings, and it wouldn't transmit anything like the power that it can when it's in tension. So it's designed to operate in tension. And that means this thrust has to be accommodated either in the motor bearings or in the thrust bearing in the pump. In the United States, motors have been developed that take the thrust in the motor, and that is the most common way it's done in that hemisphere, in the Americas. In Europe and in much of Asia, the motors haven't been developed with that sort of thrust capability, in which case we have a thrust bearing in the pump. Here, this one is for an oil lubricated one for the larger pumps, and this one a grease lubricated thrust bearing for smaller pumps. So if the thrust is taken in the motor, then we have either a 3-piece or a 4-piece rigid coupling here to transmit the thrust through from the pump to the motor. 3-piece coupling if we have a packed gland, a 4-piece spacer coupling if we have a mechanically sealed one. I'll show you that in a minute. Here it is. Here is the 4-piece spacer coupling, and this will allow you to take the mechanical seal assembly out without having to remove the motor. Here we're also showing hybrid materials are available. So, for example, if you're pumping seawater, in duplex, you might want to use duplex stainless for the wetted part, while having carbon steel for the structural non-wetted parts. Moving on to the column pipe. It's flanged column pipe with a register fit to ensure perfect alignment. They're a fabrication and they can be in any material. Bearing spiders are welded in place and they are machined in the same operation as the column flanges machining to ensure perfect alignment. There are no drop-in spiders sandwiched between flanges, even on the smaller sizes with the Ruhrpumpen design. It's usually in 5-foot or 10-foot lengths, depending on size and speed. If we're operating at 4-pole speed, so 1450 or 1750 RPM, it'll be 5-foot bearing spacings. If we're operating slower speeds than that, it'll probably be 10-foot spacings. And also, although we don't supply very many of this type of pump in at 2-pole speed, then it would be 3-foot bearing spacing, 3-foot column lengths. That would be more in a VS6 type pump. So we'll cover that in 4 weeks' time. the line shaft couplings on the larger pumps above about two, 2.5 inches, I would say, probably, then we will be using sleeved or split muff couplings. It depends on the pump heritage. These sleeve type couplings are from the Byron Jackson heritage. And these split muff couplings are from our German Ruhrpumpen Germany heritage. They both do the same job, just in a slightly different design. Now, for smaller shafts, say 1 inch, 1.5 inch, up to about 1 3/4 inches, we could have threaded type couplings. But isn't there a risk of them uncoupling if the pump back turbines? Well, let's have a look. While a vertical turbine pump with threaded couplings being driven backwards by a wrongly connected motor will loosen and uncouple the threaded couplings, a pump that is turbining, backspinning due, for example, to a failed check valve, this will not uncouple. It sounds a little counterintuitive, but let's have a look. If you take 2 bolts threaded into 1 nut, in the normal running scenario, hold the lower bolt loosely, just a little resistance, and turn the top bolt clockwise, looking from above. That's the normal drive scenario. And you'll feel the nut or coupling being tightened, which is exactly what you'd expect. Now, the motor running backwards scenario. Again, hold the lower bolt loosely and turn the top bolt counterclockwise, looking from above. And you'll feel the coupling being loosened. Again, exactly as you'd expect. Now, the third scenario. This time, the pump is turbining. The pump is doing the driving now, not the motor. It's running counterclockwise from above, so backwards, but it's being driven from below, not from above. So it's being driven in a clockwise direction from below, but still counterclockwise from above. But which side is doing the driving now? It's this side. So hold the top bolt loosely and turn the bottom bolt counterclockwise, looking from above, which is clockwise, looking from below. And you'll feel the nut or the coupling being tightened. Many pump engineers don't realize this and go specifying locked couplings when they don't need to. Yeah, a bit more pump education for you today. Now, the shafting can be open line shaft, where the bearings are lubricated by the pumped fluid, and this is usual on shallow settings and smaller sizes probably. Most commonly, though, enclosed line shaft are supplied. The inner column here isolates the bearings from the process fluid. It protects them from grit and so forth. The bearings are then lubricated with an external flush, which might be water or oil. In this slide, we illustrate water lubrication, which may well be filtered or strained pumpage or an external source of freshwater flush. And here we're illustrating oil lubrication. I have a separate little reservoir here, and it only needs a few drops per minute of oil. Here's the bowl assembly. This is for a mixed flow pump, which could be 1 stage or more stages. It would be 20 or more stages, could be on a borehole pump. A large reservoir pump will be 1 or 2 stages. Impellers might be semi-open, open, or enclosed, depending on the service. Here we show the closed and semi-open impellers. Now, which one we'll offer will depend on the heritage of the pump, the size of the pump, and the service. Byron Jackson Heritage Design water service pumps have mostly semi-open impellers. Ruhrpumpen Germany Heritage Designs have mostly enclosed impellers. It's just the whim of the designer many years ago when they did these hydraulic designs. Hydrocarbon service pumps are normally specified with enclosed impellers, although semi-open impellers can be used for them too. Now, the semi-open impeller doesn't have a lower shroud. You see, it just has the back shroud and no lower shroud. These impeller vanes seal against the impeller casing. Now, this might be integral with the suction bell mouth, or as shown here, a separate bolt-in piece. By not having a lower shroud, you remove disc friction, and this makes the impeller more efficient. With enclosed impellers, you have suction pressure at this point, and you have discharge pressure at this point, and the sealing area, the pressure breakdown area, is the entire length of the wearing, say 1 to 2 inches probably. Now, with semi-open impellers, the sealing area is the entire length of the impeller vane times 5 if it's a 5-vane impeller. This means the pressure breakdown is far more gradual and wear will be less. Furthermore, when wear does occur, you can just lower, using the rigid adjustable coupling on the surface, you can just lower the whole shaft down to re-establish the correct clearance there. Moving on now, VS2 pumps, not nearly as common as VS3. Here is the overview slide. Flows up to 18,000 cubic meters an hour, which is 80,000 gallons a minute, and heads to, well, 150 meters, which is 500 feet, as a single stage pump, or 240 meters, which is 800 feet, as a 2-stage. It has a double suction impeller, taking flow from below and from above. This leads to lower NPSH required, but as you're taking flow from above as well as below, the minimum level in the sump or inlet is likely to be the same as the single suction pump. Not as extensive a range of hydraulics as the VS3s, but when it hits a sweet spot, it's a winner. This is where they have an advantage. The volute design develops higher heads and capacities without the need for additional stages. So you can do with 1 stage of a VS2 what might take 2 or possibly even 3 stages of a VS3, thus minimizing the number of wearing parts. Here's a range chart. We'll see here the mid-range is about 2,270 meter cube per hour, 10,000 gallons a minute, at about 300 feet head, 90 meters. That's sort of middle of the range. Now, this slide shows the detail of the construction, but it's much clearer, in fact, in the next slide. Here we see a 2-stage pump on the left and a single-stage pump on the right. It's a double volute design, which means you have 4 discharges, 1, 2, 3, and 1 round the back, that combine into 1 outlet. So again here, 1, 2, 3, 4, combining into this outlet, which is the inlet to the second stage, which is a mixed flow impeller, a single suction mixed flow impeller. The next 13 slides are some case studies. I will go through them fairly quickly to allow as much time as possible for the Q&A. Those of you who tuned in early will have seen most of these in the while you were waiting session beforehand. This is the largest ever multi-stage vertical pump. I think it's still the case that we've ever made, a 60-inch pump giving 43,000 gallons a minute at 460 feet head with a 6,100 horsepower motor. Largest vertical multi-stage pump ever built in North and South America. And just recently, we've shipped another massive pump. I put a little video of this, so if you'll bear with me, it's only 30 seconds or so, but I'll go with this. Not the highest quality video, I'm afraid. In a Zoom session, we have limited memory. But this one is a 78-inch bowl diameter, 15,000 meter cubes per hour at 78 meters of head, 500 RPM, 3,800 kilowatt. And it's being installed in Morocco's largest desalination plant. So, as I say, there's the details of it. 66,000 gallons a minute at 240 feet head. Just briefly go through a few more of these. This is a 67-inch pump, 91,500 gallons a minute. That's a VS3, an axial flow pump. Here, a mixed flow pump, a 43-inch, pumping hydrocarbons. People have asked about this pipe here. This particular pump would be going in a suction barrel. It's like a VS6 type pump. And so this is a drain pipe to be able to suck all the fluid out of the barrel before it goes to maintenance. And again here. The 34-inch pump, 15,400 gallons. 28-inch pump, a smaller one, on our test bed. There's that 60-inch pump again. This is a German design pump, a TR, and the 1,000 here is the diameter in millimeters of the bowl assembly. Another German design pump, 800 millimeters. Well, that pretty much concludes the fun for today. I hope you found it useful. I just get to advertise the next of the short courses. The next one is part 2 of this session on vertical pumps, covering VS4, 5, 6, and 7. It's on the 22nd of May, which is 4 weeks today. Again, 2 sessions, one for the Eastern Hemisphere and one for the Western Hemisphere. The invitation will be published very soon, so put it in your diary. I'm going to leave the meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer will be answered within a few days. Anything you think of later, marketing@ruhrpumpen.com, or to me directly, smith@ruhrpumpen.com. We're waiting to direct your questions or suggestions to the best person to answer them, and our marketing team will be sending you the YouTube recording and the PDF of the presentation and the summarized Q&A from both of today's sessions. If you need a certificate of completion for this short course, again, marketing@ruhrpumpen.com, and they'll sort you out. And here, as usual, right at the end, are 8 slides about Ruhrpumpen to remind you of who we are and what we do. They'll be in the PDF copy of the presentation you get, so you can peruse them at your leisure. I won't bother you with them now, so that we can get on with the Q&A. So let me stop this share and let's have a look at what questions we've got. Shalindra Suratan, I do apologize. What is meant when we say that the pump is efficient in slide 19? Are we only looking at energy consumption versus outlet hydraulic power, flow and pressure, or are we also evaluating the dynamic condition while running in less efficient windows? For example, more wear, more stress, cavitation, vibrations. It's the overall efficiency of the pump as it runs in the medium that it is pumping. So flow times head times specific gravity divided by a factor to get the power of the pump. And that is the power that we measure when we do a performance test. Anonymous attendee has said, can you discuss some of the applications for these large-scale vertical pumps? What is the benefit of these type of pumps versus a standard configuration with tanks and centrifugal pumps? Well, the large pumps would be typically installed in reservoirs to pump huge volumes of water, and you just wouldn't get a horizontal pump that could do that. So that's typically where they would be used. The small Francis Vane ones might well be used as borehole pumps, pumping fresh water. They might also be used to pump water out of a sump as cellar drainage type pumps. And on offshore platforms, they would be used as seawater lift pumps or firewater pumps. Berardo Farfan says, please comment about 1, suction conditions, and 2, performance with silt fine sand laden water. With silt and fine sand laden water, you'd probably be looking at pumps with open impellers. You'd certainly be looking at enclosed line shaft to keep the bearings safe. Don't know what much more to say there. Comment on suction conditions. Well, you have to ensure that you've got a well-designed sump or inlet and sufficient submergence to ensure that the flow goes into the pump without NPSH problems or vortexing as it goes into the pump. So well-designed sump is the key thing here. Shalindra Suratan says, which one is better suitable for lifting out waste oils from sumps and transfer through header to a tank? Hard for me to say without seeing flows, heads, and full details, but waste oils, that would suggest to me like something that I'll cover in 4 weeks' time, the VS4 type pump, a sump pump probably for that sort of service. But, like I say, you haven't given me any flows or heads, so I can't really comment much more than that. Ignacio Garnero says, is it possible to add a flywheel? Not sure how to answer that. I've not come across that as a question before. I'll think about it and maybe have a word with some colleagues. Osvaldo Greco says, hi, Simon. Thank you for the presentation. Thank you. I have a large experience with propeller pumps up to 1 or 2 meter cubes per second, but it's difficult to imagine a pump with a flow of 7, 8, or even 10 meter cubes per second. I suppose a great variation in the static lift. How does this variation impact the operation of the pump? Well, the pumps have all been designed for that specific flow. So we've designed it for those flows, those heads, those power transmittals. That's why the big boys have got the experience in building these pumps. And so people like Ruhrpumpen, like Sulzer, like ITT, Gould's, they have, and Flowserve, of course, they have big pumps like these that are designed specifically for these high flows and heads. Ours are the best, of course. Uri Para says, hello, next time can you show the bill of materials of one cross-section view? What I'll try and do is get a bill of materials and put it in the attach it to the questions and answers section. Putting the bill of materials in a slideshow doesn't work very well. So I'll see if I can't get one as a PDF and attach it to the Q&A. Anonymous attendee says, are there specific models you typically see for geothermal borehole type applications? Yes, geothermal pumps are Francis Vane, relatively small pumps generally, and they go down to quite significant depths. We've also got VS1 pumps in molten salt service in geothermal type ones, and that's quite an interesting design. The anonymous attendee is back and says, thanks for the info. This subject was too advanced for me to attend your earlier courses. What shall I do, or at least to have their slides? Right, the earlier courses are all available on our website. I think I showed at the beginning of this presentation that you can go to the ruhrpumpen.com website and follow the links to short courses. And all the courses there are listed, and you can download all of those materials at your leisure. Brian Fox says, are fire pumps available in VS1, VS2, and VS3? Absolutely. We do a lot of fire pumps, especially for offshore platforms, which are VS1, VS3 type pumps. I don't think we've done any VS2s, I think, as fire pumps, but VS1s and 3s we're doing all the time, both in freshwater service and offshore platforms. What else have we got? At the moment, that's all the ones that I've seen. Let me just leave it open a few seconds longer to see what we've got. If any more come up. 10 to 6 here, so still 10 minutes before beer o'clock, so maybe I had to start off early. It is a nice day anyway. Oh, I think another one's popped up. Yes, here we go. That'll take us through to 6 o'clock. Oh, anonymous attendee said, excellent presentation and info, Simon. Thank you very much. Well, that's all I needed, because that's okay to have a beer. So I'll call it a day there. Thank you very much for attending. I enjoyed preparing and presenting it. Hope you found it useful. See you on the 22nd of May for part 2. We'll be looking at VS 4, 5, 6, and 7 type vertical pumps. Bye-bye.